Okay, we're looking at Lab 10. We're going to focus on the quasi-geostrophic height tendency equation this week. We've been talking a lot about the QG equations of motion using the vorticity equation to help diagnose divergence, using the thermodynamic equation and the omega equation to help us understand omega. But there's another version of this equation set that allows us to basically forecast the future height of a constant pressure surface, and it's this QG height tendency equation. So the data are available on Scholar. So we use the ThinLink Scholar interface and basically source the usual setup file to get Nmap2 started, and look for a set of restore files under restore data settings in the upper left corner of the data selection window. If you load that up, it should give you all the loops that you need. So there's 5 different loops that you'll look at for this lab, and they should be in the different loops, which you can access using the middle loop selector and change between them, or using the function key is F1 is loop 1, F2 loop 2, etc. So we'll go through the background material for the QG height tendency equation, and then there's questions for the lab, so please enter your answers and export this as a PDF before you turn it in to Blackboard. So the QG height tendency equation, going back and looking again at this overview of the QG equations, this is a simpler version of the equations of motion, where we're neglecting small terms that aren't important for synoptic scale flow and just keeping the big terms. So this is the case if we have weak acceleration. Okay, it's not zero acceleration. Zero acceleration would be just pure geostrophic flow. So there's some acceleration, which means there's some ageostrophic flow and some vertical motion. And so we're looking at Rossby number, this ratio of acceleration to the Coriolis force of about 0.1. And if we combine the vorticity and thermodynamic equations, we can get the QG omega equation, which we've looked at already. And notice that this is a diagnostic equation. There's no time derivatives in this equation. Okay, so we've got the second derivative of omega, we have the height derivative of the geostrophic vorticity equation, and we have the horizontal second derivative of the geostrophic temperature advection, but there's no time derivative. So what this means is that the response and the forcing are simultaneous. Basically, they're connected to each other. It's not that the forcing occurs and then a few hours later the response develops. These are simultaneous, and this allows us to diagnose the vertical motion. But it's a diagnostic equation. It's not a prognostic equation. We can't do prediction with this equation. So we can combine the thermo and vorticity equations in a little bit different way and keep a height tendency, keep a time derivative of the geopotential height, basically the height of a constant pressure surface, and use this to predict the future heights. And so this is called the QG height tendency equation. And it looks like this. So you can see there's a lot of similar looking terms as we went through in the omega equation, but it's a little bit different. So again, we've got the static stability parameter that's showing up at least in the denominator of one of these terms, as well as the fancy second derivative operator here. But let's look at this equation term by term. So the left-hand side has a lot of similarities to the omega equation. It has this fancy second derivative that's operating now on d phi dt. And so phi is a geopotential height. That's g times z. So basically this is the height tendency. And we're looking again at this, we're assuming this sort of a wave-like pattern. So if the height tendency is wave-like, the second derivative acts like a minus sign. So we approximate this basically as minus 1 times d phi dt equals the right-hand side. Okay, so if the right-hand side's positive, we would expect a negative height tendency, or height falls. And if the right-hand side's negative, we would expect height rises. So let's look at the right-hand side. The first term, working our way from the inside out, we've got the geostrophic vorticity that's being advected by the geostrophic wind. So this is the geostrophic vorticity advection just multiplied by the Coriolis parameter. And that's just going to be a positive number. So basically we're just looking at the geostrophic vorticity advection. So there's no other weird derivatives of this. It's a pretty simple term. And if we have positive vorticity advection, then we'd have a positive right-hand side. We would expect the left-hand side to be negative. So height falls are associated with positive vorticity advection. Height rises are associated with negative vorticity advection. And that's the vorticity advection term. The second term, you can see it involves minus Vg dot del T, so that's the geostrophic temperature advection. And then there's a minus d by dp of that, right? Remember F naught squared is positive. Sigma is the static stability parameter, that's positive if the atmosphere is stable. So we just have a positive number. We're basically looking at minus d by dp. So we're taking the vertical derivative of what's in the square bracket. And the trick is, if we see minus d by dp, we should be thinking plus d by dz. So how does the geostrophic temperature advection change with height? That is the second term. So again, if this term's positive, we should see height falls. And so if the temperature advection is getting more positive with height, we should see height falls. If the temperature advection is getting more negative with height, we should see height rises. And it's really the sum of both of these terms that's important. And so we have to figure out both of them, add them together, and that'll give us the answer. So our height tendency multiplied by minus 1 is equal to the geostrophic vorticity advection plus the geostrophic and temperature advection change with height. And if that right-hand side's positive, we should expect to see height falls. So our time tendency of the geopotential height should be negative if the right-hand side's positive, and vice versa. So let's take a look at our advection. We're thinking about advection by the geostrophic wind, and we can visualize that by looking at the height fields along with whatever it is we're advecting. So let's say we're looking at height contours are solid, and maybe temperature contours are dashed, or vorticity contours are dashed. And we're interested in the advection by the geostrophic wind. Well, in this case, if the heights are higher below, lower above here, the geostrophic flow should be going from left to right. And it's bringing in higher values along with it. And so this is an example of positive advection by the geostrophic wind. The second example is just the opposite. we still have lower heights on top, higher heights below. But let's say it's temperature this time. The lower values of temperature are here, higher values of temperature are this contour. The flow is going from left to right, so it's bringing lower temperatures towards the right. And this is an example of negative advection by the geostrophic wind. In both of these, notice how these height contours and parameter contours, either temperature or vorticity, form a box, like a parallelogram. Well, the area of this box is going to be inversely proportional to the advection. When these lines are all really close together, we've got a really strong gradient. We're going to have strong geostrophic winds and a strong gradient. We'll have much higher values of advection. So we need to be able to get very comfortable with looking for these sort of intersecting contours between the heights and temperature, vorticity, whatever it is we're advecting, to be able to visually identify areas of strong advection by the geostrophic wind. And that's really the key to be able to use the QG equations to either diagnose omega or to do the height tendencies and do that height prediction. So let's go through an example. We need to determine the temperature advection and see how it changes with height. So we'll start, and we're going to try to diagnose what's going on at 500 millibars. So in order to see how it changes with height, we need to go below 500 millibars and above 500 millibars. Do a sort of centered difference approach to see how the temperature advection changes with height. So let's start at 600. The solid white contours are the heights, and the dashed kind of magenta color are the temperatures. And we got a cyclone. You can see the cold air, the warm air. So you can start to see these intersecting contours, these boxes that I talked about. This is an example of cold advection, and here's more of these boxes intersecting. Here's an example of warm advection by the geostrophic wind. And we can get Nmap2 to calculate this for us. And so the warm advection are the positive, sort of warm colors here, and the cold colors are the cold advection by the geostrophic wind. So now we need to see how this changes with height. So we need to move up to a higher height, a lower pressure, 400 millibars. You can see now these height contours are pretty much parallel to the isotherms. There's a little bit of some advection. It's kind of tough to visually interpret this, so let's let the computer calculate it for us. And you can see we've got some weak warm advection in the northern plains, and some fairly moderate warm advection down, say, Arizona, New Mexico, to the south of this trough. Well, we want to see how things are changing with height. So if we go back, at 600, this is the lower level, we actually have some cold advection that gets weak, and maybe even no advection at 400, and then say here in Arizona, we start with basically no advection, and it gets more positive as we go up to 400. So it looks like throughout this region, the Four Corners area, Colorado, New Mexico, Arizona, we actually have temperature advection that's getting more positive with height. And if we actually calculate that vertical derivative, we see that we have this positive term. So this is the temperature advection changing with height term, basically what we call the differential temperature advection, the vertical derivative of the temperature advection by the geostrophic wind. And sure enough, it is positive throughout this region in the base of this trough at 500. So next we need to look at the vorticity advection term. And that one's just simply what's the vorticity advection? Is it positive or negative? So here's our trough at 500. We have a vorticity max at the base of this trough. So we would expect the geostrophic wind to be bringing more positive values on this side, and positive vorticity advection, say in the Colorado and New Mexico, and then the geostrophic wind bringing more negative values, lower values into Arizona, negative vorticity advection on the backside of the trough. And if we calculate that, sure enough, we see this dipole of positive, negative vorticity advection, warm colors being positive vorticity advection, cool colors negative vorticity advection. And again, just this term by itself, we would expect to see height falls ahead of the trough, height rises behind it. But we need to combine both of these terms together. And so if we basically sum the vorticity advection term with the differential temperature advection term, we get this. And so the warm colors are basically saying that the right-hand side is positive. The cool colors saying the right-hand side is negative. And the height tendency should be the opposite sign. So we should expect to see height falls in Colorado and New Mexico, and then height rises in Arizona, Southern California, Southern Nevada. So let's actually check and see. Here's what the 500 millibar height looks like at the current time. And let's step forward in time by 6 hours. You notice that the heights fell in Colorado and New Mexico, and the heights rose back in Arizona and Southern California. So we can compare these two. You can see that the trough basically moves to the east and the heights fall, and a ridge moves in behind it and the heights rise. So this is the kind of thing you're going to look at in the lab, calculate all these different terms, and then check to see how well it works with an actual forecast example.